Hey everybody, this is Larry. This is me going with Q4 of the weekly Leetcode daily contest. Weekly contest 233. Count pairs with XOR in a range. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. So this is a hard problem. It's greedy. It's very competitive programming. On an interview, it has components that you would care about, but XOR is always a little bit awkward to be in general. So don't feel that bad about it. This is a weird-ish, awkward-ish problem. Let me know what you think. And yeah, during the contest, the idea is just having nodes and then greedy, right? There are a couple of things to note. Let me kind of bring up Paintbrush real quick so I can do some drawing. I've been trying to be a little bit more about drawing, especially for tree problems. So hang on. Okay. So this one, for example, so we're gonna use a trie. What is a trie? A trie is just basically a tree that has values on the edge. And for me, every number, we're gonna break it down into a trie. So let's start with going through an example. So for example, you have a 9. 9 in binary is what, 8 and 1. So 1 0 0 1 1 2 4 8. Yeah, right. So then in a trie, and for now we're gonna keep it to 4 bits because I'm not gonna draw way too much things. But the idea is that, okay, you have a root node, you have edges, 0 and 1, dot dot dot, right? And here for 9 we create one. Let's erase this left for now. I know it's really ghetto. And then basically you create, this this trie path, and yeah, and then you kind of keep on doing it, but as you incrementally do it, it's just about greedy. And ordering actually doesn't matter. You don't have to sort it, but the idea is, okay, I know that we have to get it within a range, but let's ignore the range for a second and just focus on getting an upper bound, right? So now let's say we have an upper bound. I'm drawing it on a mouse, so excuse me. But yeah, let's say we have an upper bound, and let's say we have a couple more nodes. Let's add an 8 node. An 8 node is 1 0 0 1, so this is actually the same, but with a 0 here. Let's add a 4. So 4 is 0 1 0 0, so that's a 0. And then this is a little bit awkward, but 1, and then 0 0, right? So then and then the question is, okay, let's say you have an upper bound of 5, right? This is kind of in the example, but not really. So then, and now we're trying to add a number. Let's just say, let's just do 7 because it's funky. I don't know if this is a good example, but it's 7 in 4-digit numbers will be 0 1 1 1 1. So then we ask ourselves questions as we go through, right? Okay, so the upper bound is 5. So what does that mean? So that means that the first path we want to take. Let me change the colors real quick. Okay, so that means that, let's say we're at this node right now. What does that mean? That means that the upper bound is 5. And 5, of course, in binary, it's going to be 0 1 0 1, right? That means that 1 bit at a time, let's look at the first number with 0, right? 0, that means that we're good. So then let's go down this left path. And let's go down this left path, right? We could ignore everything on the right side because they're never going to be the answers, right? Yeah. And then the next one is going to be, and then the next number is going to be 1, this one. And, you move the nodes 1 at a time. These ones are 1s, so we go the same path again. So maybe this is a bad example, but we go the same path again. But one thing to notice, one thing to notice is that we go down the 1 path, right? And what does that mean? We go down the 1 path because we know that the 1 XOR 1 is good enough, right? But what happens if we try So basically now we do a progression upper bound, lower bound situation, right? So let's step back a little bit for a second. Let's say here, right? What does it mean going down this path? That means that, you know, the range of numbers that we're looking at now are, you know, from zero, the first number has to be 0, right? So that means that the range of numbers that are in the tree will be from here to 0, 1, 1, 1, right? So basically, and what does that mean? That means that these numbers will give you 0 to 7, right? And basically, we're trying to maintain the invariant that the upper bound is going to be 5, right? Yeah. And now when we go down the 1, however, you know, that means that everything here to the right side, it's going to give you oh wait, no, sorry, I think I messed that up. Okay, step back for a second. Okay, so now what happens when you go to the second number, right? So the second number is actually a 1 on the upper limit. And what does that mean? That means that the two variations, right, on the possible numbers that we have, you know, let's say we still have 7 here. There are two possibilities, right? Let's say, you know, let's say we go down the left path. What does that mean? That means that it's going to be 0, 0, dot, dot, dot. And that means that, you know, if we XOR all these numbers, we're going to lead to a prefix of 0, 1, dot, dot, dot that we look at, right? And that, what does that mean? That means that these numbers we have to consider, because for tie breaking we have to think about the suffix. However, if we, let's say what happens if we go down to the right path? The right path, you know, we now have let's say we have a right path. Right path, we have, you know, a 1 here, and that means that all the XOR answer is going to be 0, dot, dot, dot. What does that mean? Well, it turns out that every number here with a prefix of 0, 0 is going to be less than this upper bound, right? Can you see why? Because that means that the prefix is 0, 0. It means that no matter what happens in the suffix here, everything is going to be lower than the upper bound. So that means that we only have to go down the 0 path, which doesn't exist, because we know that all this subtree is true. And then the answer is just pre-processing the try in a way such that we do the count in an efficient way, so that we don't, because if we do a naive depth first search of every node, it's going to go n squared, because you're going to look at each n node once or something like that, right? It's going to be too slow, is the short answer. And in this case, n is big. N is 2 times 10 to the 4th. I mentioned that a little bit late, because obviously if it's n squared, you just do n squared. But this is a Q4, and you know why you're here, because n squared doesn't work. But yeah, so here we see that the entire subtree is correct, so we don't even have to go to it, and we just have to go to the left. And because the left doesn't have any node, that means that we don't have any more considerations. But let's say, for example, if there are more nodes, right? What does that mean? If there's a node here, then we, you know, then that means that this is a 0, and this is this 1, and that means that we have to consider tiebreakers. Yeah. Okay, you have to consider tiebreakers. My writing is going to be too slow, but I just write out considering tiebreakers. So that's basically the idea. It's greedy, and it's about removing subtrees at a time, so that, you know, everything happens in log of x time, where x is the number. Okay. I know that this explanation isn't perfect, but we're going to go over it with respect to the code, and then, you know, hopefully we can kind of, you know, because I hand wave a little bit about some of the pre-calculations. So yeah. Oh yeah, one more thing that I want to add is that, let's add it on top of this as ASCII code. One thing that I would add is that, because this, so you have some, you want to figure out the f of low high where some, there's some count where where some low and you want to count the answers between this, right? And it turns out, because this sequence is monotonically increasing, you can imagine that going from low and low plus 1. Let's say you have low to low, or let's say we have 1 of low and f of 1 of low plus 1, right? Well, in this case, you can see that low plus 1, it's going to be strictly increasing, or sorry, monotonically increasing, because it has to be greater than or equal to, right? Because it could be equal to, but it has to be strictly greater than, and ... right? And as a result, then now you can think about this sequence as basically 1 to 2 plus, okay, so you can think about f of low to high is equal to f of low to low plus 1. And what does this mean? Okay, maybe another. What does this mean, right? Plus f of low plus 1, low plus 1 plus ... plus f of high, right? And what does this mean? This means f of low is just one number, right? This means that this is the exact number, the count that is exactly equal to low, right? So that's basically the idea. And from that, you can see that one, you have to do some math, but low high is equal to, and you do some math around algebraic subtraction, and you would get something like 1 to low. And again, we established that low is the sum of this, so then it is just that, right? And see if you could prove this. I think so this is a technique that is very helpful for this problem, because then now you don't have to do in between. You now because of this 1, or you could do 0, maybe it doesn't matter. Maybe 0 is more intuitive. By the way, that means now we can reduce this problem of going from low to high inclusive to one where we just look at the upper bound, and then we could break it into 2 different problems. And that's basically the idea that I go with. Let's kind of go for here. And I have some issues with debugging, but basically this part should be basically what I said. I would go from high to low minus 1, and then we subtract the difference because we want to keep track of low. And then here for each one, we start with a try. We start with a count is equal to 0. We do a count, that the algorithm that we talk about, which we will talk about again, don't worry. And yeah, and then after that we add the x to the try, so that it can be considered in the future. So this idea is of course similar to prefix problems, where like prefix dynamic programming or something like that, almost, where you do a count on the prefix. So yeah, so that's where the similar idea as well. I have some abstraction here. It's not as clean as abstraction as I would like. Let me make the file a little bit smaller so we could fit in one screen. But basically, okay, let's do the nodes first. Node, I just keep track of 2 things. So each node will have an edge lookup, which just basically have 0 or 1. We don't preemptively create them because just in case, I guess, because you don't want to create an entire tree. And then the count will return the number of nodes in that an entire subtree, so that we could terminate early, so we don't have to visit all the way to the leaves to do the count. And here on the try, we declare the root as a node, and for an add, we look at it from we do the math. I did the 16 because 2 to the 16 is bigger than 2 times 10 to the 2 times 10 to the 4th, which is in the constraints. And yeah, so we do an index that way, and yeah. but we look at the most significant bit one at a time, and to get the edge, if this node doesn't exist, we create it, and we also add a count going to that subtree so that we kind of pre-calculate the count for that subtree, and then we just go down that subtree. So this is almost like, you could think about this almost like a depth first search, creating a node at a time to go get to the leaf, kind of. And then the count part is the more interesting part. I did it with case analysis. I was a little bit slow on this one, but basically this idea is the same. We look at, each node at a time, and you can watch me solve this live during the contest, and I actually say it out loud. Okay, let me break down the cases, right? And this is how I broke it down. For example, if now is 1, and we look at the high bit, and if 1 is equal, if there's nothing in that subtree, we just return early. Otherwise, we go down that subtree. If they produce a 1, right? So the key thing to note is that the two scenarios that are a little bit different, because in this case, now XOR high now is equal to 1, right? Oh, sorry. Actually, going back, right? High equals to some tree node is, is we want it to be less than or equal to high now. So that's basically the idea. This is what we're searching for. Let's say X, and then we work backwards, right? We can move the now XOR function to the other side, because that's how that's kind of how addition works in XOR. And then now everything follows through, where if we have this case analysis where if high now is equal to 1, or if this right part is equal to 1, that's basically my idea here, right? If this part is equal to 1, then we just go down, if the edge is 1. Maybe I explained this a little bit backwards. Sorry. But yeah, if the high now is 1, then we want to count. We basically greedily go down the path that lets you, go through the other answer, right? Because basically, if this thing constructs a 1, we want to also count the 0 path, right? And that's where this comes in, because because this path is such that now XOR X is equal to 0, right? Because if high now is 0, that means that X has to be 0, and that means that if now is 1, then X has to be 1, right? And that's why we have to go down this path. Hopefully that's a better explanation. And in the else, well, if now is equal to high now is equal to 1, then you have and now is equal to so now is equal to high now, and if now is equal to 1, high now is equal to 1, X can be 1 or 0. Oh, sorry. And we think about those two cases, right? If X is equal to 1, then 1, this is as we talked about before, the left side is going to be 0. And in that case, we want to count the entire subtree, and we can do this without going into it. You can think about this as a depth first search, but we're terminating early and just summing all the subtree, right? And then on the right side, well, we just move to the right side to kind of get the tiebreaker. So this is all very case analysis-y. Hopefully that makes sense, or at least it gives you a good idea to know where to start. It is a very long explanation because it's very tricky. So yeah. So that's basically the idea. Yeah, let me know what you think. Yeah. Whew. Sorry, let me take a breath because I am recording these live. So what's the complexity of this, right? So here, we're just gonna, well, we do 2 of these go operations, so it's gonna be constant times the cost of go. What's the cost of go, right? for each number, so this is going to be n, this O of n numbers, the count, if we look at this count function, because we only, for each depth of the node, we only do O of 1, for here, well, this is going to be 16, O of 16, which is technically O of log of high, let's just say O log h. And here, for each loop, you can see that we do O of 1 operation because we only, you could see it. I don't want to get into it that deeply as to why. But you could do it, you could count every operation and it's O of 1. So basically, so this is going to be O of log h times O of 1. So that's, that's a little bit awkward. So this is going to be O of log h, and that means that count will always be O of log h, right? And in a similar idea, add will also be O of log h, or in this case 16, as we said. And that's basically the idea behind this function as well. You just go, this is just iterating through the depth. So basically going back here, you have O of log h and O of log h. So in total, this function is going to be O of n log h for time complexity. And for space complexity, you can imagine that for each node in a tree, we have at most h depth. So it's going to be O of log h depth, because h is the maximum number. So yeah, so it's time and space as well. Because for the node, there's going to be one node for each log of h, and just n nodes or n numbers. So it's going to be n times log h. That's all I have for this problem. Let me know what you think. And you can watch me solve it live next. Come back to it. Let's see if there's a real problem. Them are nice pairs. It's going to be a try problem. Maybe. This is not that bad, because you can just do the high and then, okay, I think I got it. Because you do a try on the high and then you do the try on the thing. Okay. Okay, I think I got it, but it's annoying. Okay. I'm surprised 2 people got it already. It's maybe not. I don't know. I don't want to do this. Maybe no. I doing? I hope this is fast enough because I had issues with that earlier. Okay, and then now for x in nums. Okay, so okay. Okay. So inclusive. Okay, for x in nums. How do I add? Maybe I'll separate it out. So we want the most significant bits first. What is 2 times 10 to the... So that's what? 2 to the 13? Nope. 2 to the 15? 2 to the 15 is fine. 6. Let's do 16. Yeah, okay. Now let's go to we maybe okay. You go no. Okay. That should be roughly it. And then count. Oh. How many people have gotten this yet? Okay. Doing okay so far. Could have been faster in Q2, or not the wrong answer. I have to save a thing. and also this is wrong, I think. But if now in current we add 1, and then also maybe okay. This is annoying to think about, but it's fine. So basically we want to match so that's the first base one, like if I now okay, if now is equal to 1, it's just case analysis. High now is equal to 1, then of high now is equal to 0. Then we return count because everything is going to be no, is that true? What am I thinking? Okay, think. Let's have something like this, and then the high is something like this. What happens, right? Well, then we want to bring it to 0. So if now is now, if high now is equal to 0, then we want to make it a 0. So we want to go down the 1. Okay. And we want to add the other one because wait, what? Do we? Because if this is 0, then we want to make it a 0. But then the 1 doesn't, we don't care about the 1s. Okay, fine. Else we want to go down to 0, because if high now is equal to 1, if this is 1, we're good, but then we also count is equal to current attributes dot count. Okay, because we want to add the other side. Okay, and then else if now is 0, if now is equal to 0, so they're both zeros, so we ignore. If they're both zeros, then we want a 0. And we ignore the other one, but then here that could be a dangerous typo, but is this it? Maybe, but not yet. Oh, yeah, where am I? I need to do some checks. Yeah, okay. If one not in current, we return count, I think. Oh wait, this is actually awkward. I think I will return the other one. Like, cause if 1 is 1 and this is 0, then we want to include all the other. Okay, yes. Oops. Yeah. If 1 in current edge. There's no more path to go down. Okay. If 0 not in edge, return count. If 0 not oh, whoops. Man. Really sloppy today on all these things. Node is not irritable. Where am I doing that? 17. Oh. I'm missing a lot. Oh, I don't return the answer there. Where's my add? Oops. 4 and 8, is that right? Nope. 6 and 8. Let's print it out real quick. Oops. Uh, 4 and 0, so that's already wrong. Oh wait, no, that's so we want a 6, right? So that's definitely wrong. Because if we eliminate something, but that's unfortunate. I mean, I think the logic is right. I'm just doing something weird, maybe. I think I'm undercounting, but I can't really prove it easily. I mean, I'm definitely undercounting because there should be at least 6, right? And there's only, is there a case you can get it 2? No, because this is all, yeah. Okay, so 1, 4 to 7. Wait, what? Oh, I was looking at the wrong one. Okay. Oh wait, no, I'm looking at the right one. This is gonna be a sad day. Okay. We're looking at the first problem. Okay, yes. So we want to look at this 6 and why we're not returning more. And we call it twice because we printed twice. That's why it's a little confusing. Okay, so 1, 6, yeah. This is okay, this one maybe okay. Yeah, I think that's okay. This one is not okay. Because this is at least 2. Why is this wrong? So, okay. That's annoying. Let's see if I see anything obvious. No, I mean, I don't think so, but I could be wrong. Yeah, okay, that's So we go 0, 0, 0, 0, 0, 0. That makes sense so far. All the way down to what was the 4, 6, and 1? 4, 6. So we want to do the 4. Do I have to sort it? I don't think sorting matters in this case. But the 2. So why not? That would be magic if that suddenly works. Yep, still wrong. I didn't expect that to matter, to be honest. Because it's XOR. Alright. Okay, so the 2 is here. And the magic is starting here, I think. That's out of count. Debugging on this is murder. So we want here. Oh, 2 only found 1, but so the second index only found 1 number, but it should have 2 number. Do I miscount? I misunderstood the output for a second. So it's missing 1 number. It goes all the way to. Yeah, this is the first part where it's tricky, where high the now is a 0 and high number is 0 to 1. So that means that we want to we want to add everything in a 0 path. Okay. And also, I'm not sure that this is not double counting, to be honest. But we want to add everything to the 0 path. And then I think at the very end I'm missing off by 1 maybe. So that looks good maybe. And we add the 2. So then the next one we go to the 1. The 4, what is the 4 doing? So it is going to the 1 and then it is going to the 6, right? Oh, I see. So after, no, that's not right. No, it's fine. Maybe. So it what is this one represent? What does this one represent? Goes to the one. I have to think about it. So we have our tree looks something like this. We have a 4 and we have a 1. And then when we add a 2, we want to match this. We have a 2, so it's this. And then what happens? So we have a 1. Oh, we have a 0 and a 1, so then we add this part. That's good. And then we follow the 1 path. And then now we already counted for this, but if this is a 1 and then this is a 0, we return count here early. Is that true? Because we want is 0. Okay, so we do here, right? And we don't early because we do have an edge, right? No, wait, what? Yeah, no. We do follow this, and then we have 0, 0, and 0, 0. We have here, and then we have this thing, and then now we're at the very end, and we don't count for that reason. Huh? How do I adjust for this particular piece? Maybe something like that. Am I really just that sloppy? 6, 8. Answer matches. I always spend a lot of time debugging, so I might as well just YOLO submit it. Because if it's wrong, then we get an answer. Yikes. Hopefully it's not time limited, because it shouldn't be that time limited. But maybe I'm, okay, good. So I had a minor typo, I just didn't think it through all the way. Yeah, thanks for watching. Let me know what you think about this problem. If it was good, bad, I don't know. This was a interesting contest. Let me know what you think. Hit the like button, hit the subscribe button, join me on Discord, ask me questions here, there, wherever you like. And yeah, have a great week, have a great time. Stay good, stay healthy, stay well, and to good mental health. I'll see you next time. Bye bye.